In this section, we are going to transfer the notion of limits from sequences to functions, which is kind of an extension of the definition that we've seen before. But before we do so, I want to do a little prelude inside this section, because this is now something, I want to make something explicit, which we've kind of used all the time, basically, but without noticing. And I want to discuss some little aspect a little bit, and because this fits in nicely, as we shall see soon. Okay, first of all, like the motivational observation for this prelude is that continuity is a local notion. And this is what I want to make precise. What do I mean by this? Local always means that with this back to some point, something is locally true if it's true for all points which are sufficiently close to this point. So while kind of, sometimes it goes to continuity, because if I want to check if a function is continuous at a point A or not, all I need to check is kind of what the points very nearby are doing. Because remember, there's basically this idea that some delta in this definition, so for all epsilon there is a delta, and this delta means that all points which are kind of delta close to our point where we want to check continuity. And the idea is kind of that we can always find some delta, and so this means we can always find points nearby with so that points nearby have nice properties. But this the continuity at the point A doesn't make any statement about points which are kind of far away. So continuity really depends only on things which happen nearby this point. And this is what I want to make precise next. And for this I need to introduce some new terminology. But this locality of, so the local notion of continuity, we shall see what I mean by this. Okay, so first of all, some definition, just some terminology I need to introduce to formulate the kind of the corresponding result properly. So assume we have some D subset of C, which is kind of later on supposed to be our domain of our function, and we have some point x0 in D. Okay, then A subset of D, so if we take a subset A, subset of this D, is called D neighborhood, D neighborhood of of x0, if the following holds: if there exists some r, some small positive number r, such that the set BR of x0, which I shall define in the next line, intersected with D, intersected with D is contained in A. And here, second part of the definition, basically, BR of x0 is defined as the set of all x and c, such that x minus x0 to the absolute value is smaller than r. Okay, so this is, if you take a look, this is kind of the space of points. If you can understand this definition here, or this inequality here, the set of all x which are kind of whose distance to x0 is smaller than r. So it's kind of the inside of a circle. So if we're here and we have a point x0 in C and we have some radius r, then this would basically be the inside of this circle here. Right? All points which are outside on the circle, they're not included because their distance is equal to r, but everything which is inside. So this is BR of x0. Okay, so with that being done, what does now this definition mean? So this definition means A is chosen such that we have some open, like say A, let me just draw some set A. This could be any subset of D. So we can find some circle which is kind of completely inside. So this means kind of all around x0 we have some space inside D. Right? So we can move a little bit in every direction. And this is kind of what we, of course, need to formulate if something's happening very close nearby. So we need to be in some neighborhood of this point, so that we have all points nearby of, so I mean the neighborhood can be very small, but somehow there's some room to wiggle all around our point x0 that we are considering. Okay, so remarks 340. So I've introduced a similar notion, namely dr of x0. What was the difference again? So br of x0 is all points inside a circle of, as I just said, of radius r around x0, and dr all points inside the circle of radius r around x0 and on the circle. Circle of radius r. So the distance between dr and br of x0 is just that the outer line is included in one but not in the other. Okay, this is a neighborhood. Next thing I need to define, second remark, almost forgot it. So using these b deltas, br of x0, we can formulate the continuity a little bit different, because this inequality, this looks pretty familiar to what happens in the definition of continuity. And so I can just write down the definition of continuity once again. I can never write this down often enough, but this time using these open balls, namely open disks. The correct notion is then, so f from D to C is continuous in some point A if the following holds. For all epsilon bigger than 0, there exists some delta bigger than 0 such that, so far nothing changes, f of x minus f of a is smaller than epsilon. This you could also write as a disk, but I don't want to exaggerate. But that this holds for all x which are whose distance to a is closer than delta, and this means for every x inside b delta of a and intersected with our domain, because otherwise this would be well defined. So this is a bit maybe more concise. So this is just continuity. Of course, this could also be formulated by saying that f of x is in b epsilon of f of a, but this is good enough for us. So here's where really these open circles appear. Okay, next part of terminology I need to introduce, definition 341. Okay, so very general, we take some sets and a map between sets. X and y are sets, and we have some map f from x to y. This is a map, and we just take some subset A of x. Now, two very elementary notions that I just haven't defined before, not because I couldn't have done it, but because I just, I could have defined this in chapter 1, but I just didn't need it, so now let's do this right now. We get another map, namely f, and we now take this long bar and write an A as an index. This is called the restriction. So this is how we always note restrictions, namely from A to Y. So A is a subset of X, and this simply means we consider F, but just defined on A. So we just shrink the domain and do everything as before. So F, just formally F restricted to A. This is how you always speak the symbol. I have no idea if this has any other name, but F restricted to A of X. This is just simply defined as F of X for all X in A. Okay, and this is called, as I just said, the restriction of F to A. Okay, so we just shrink a map and by shrinking its domain. Now the counterpart to this, the counterpart to restriction is a so-called extension. Assume we have a map which is defined on A, which I call G. So G is just some map. Be a map. F is called. So F is defined on the whole thing. X is called an extension of G. And now this is kind of pretty logical what happens now. So the extension of G, if we take a point in A, then F is just simply given by G. So F of X is equal to G of X for all X in A. And in this notation that we just introduced, this is the same as saying that F restricted to A is G. So it's G on the part where G is defined and something else on the rest. So just an extension. Okay, so a lot of definitions, and I only have to erase again. So yeah, let me quickly erase. Now I want to bring the formalism I just introduced in connection to continuity, and this kind of formalizes this notion from the beginning that continuity is something local. Namely, so theorem 340, oops, sorry, 42. So we have some domain D subset of C, and we have F, a map from D to C. Whoops, this isn't really an arrow, okay, sorry. From D to C, we have a subset A of D and a point A in A. Okay, now the first part is not too exciting. If F is continuous in A, then the restriction to the subset, F restricted to capital A, this is now a map from A to C. This is continuous in A. Okay, so much for that. But now comes the interesting part. So if we make an additional assumption, namely if we assume that A is a D neighborhood of the point A. So A contains all points in the domain which are close to A, or yeah, like reasonably close to A. Then this here becomes an equivalence. Then F is continuous in A. In A, if and only if the restriction is continuous in A. And this is now the interesting observation. This says that continuity is something local. Whenever I want to check that F is continuous in A, I just need to consider F on some neighborhood of this point A. So I just need to restrict to points which are sufficiently close there. They can be very, very, very close, but you just need some points around so that we can do this. And so this means this is enough to get continuity. So it's really a local notion, so to say. Okay, proof. The first part is actually almost trivial. So, we want to show the restriction is continuous. So we take some epsilon bigger than 0. Since F is continuous in A. This means we get a delta bigger than 0 such that f of x, maybe I can get this right here, f of x minus f of a to the absolute value is smaller than epsilon for all x in B delta of A intersected with the domain D. Okay, but we know that A is a subset of D. So in particular we get f of x minus f of A to the absolute value smaller than epsilon for all x in B delta of A intersected with A. Simply because this is a subset of this set. Okay, so this means, now we've got it. We found some delta such that this is satisfied. And so since epsilon is arbitrary, this shows that f restricted to A is continuous. We're already done. So this was easy. Now for the other part, we just need to make a simple observation. So, we let, no, sorry, wrong direction. I wanted to, B, of course. First of all, the one direction I need to mention at least, this is obvious because so now from there to there, this is now part A. So that's a special case of part A. So it's only the other implication that we need to discuss at this point. Okay. So for this implication. Okay, we start the same way. First of all, I need to introduce some notation. So I know that by assumption A is a neighborhood. Oops, yep, still is visible, okay. A is a neighborhood. So this means we can find some r bigger than 0 such that B r of x0 intersected with D is a subset of A. So this particularly means that BR of A intersected with A, okay, that this is everything here, everything from there. So this is the same as BR A intersected with D. Okay, this is some fixed value R. And so this we can now use to see that we can just use the definition of continuity and maybe shrink our delta a little bit that we need to choose to get the right idea. Okay, so yeah, since this holds first of all, since this is the same, and if we now would take a smaller radius, what would that mean? So if we would take some radius which is smaller than R, this would mean that we take a smaller circle, but if these two big circles have this property, then the smaller circles will have this property as well. That's obvious. So this means that BR prime, let's say A intersected with A, is the same as BR prime of A intersected with D. For all R prime, which are bigger than 0 and smaller than or equal to R. Okay, this is easy to see. And now this will be enough for our argument. Now we start as usual with continuity. We take some choice of epsilon. Since F restricted to A is continuous in A, so we get we get a delta bigger than 0, such that f of x minus f of a to the absolute value is smaller than epsilon for all x in B delta of A intersected with A. So now we don't know if this delta is small enough such that this property here holds, so that delta is below this value of R. Okay, so what do? We kind of artificially shrink this delta, because of course we can just take a smaller delta. This wouldn't change anything in the argument. We just need that there exists some delta. And we shrink it such that it does the job we want it to do. Namely, we take delta prime to be the smaller of the two values, the minimum of delta and R. Now we know, so this is of course again a positive number. And now we of course know that it's kind of smaller than delta, so that this holds if we replace delta by delta prime. But now we have this property here as well, since our delta prime is now inside this interval. So this means basically that we're done. So we know that B delta prime of A intersected with capital A is the same as B delta prime of A intersected with D. And hence, since delta prime is smaller than this shows that f of x minus f of a is smaller than epsilon for all x in B delta prime of A intersected with A. But here we've seen that this is the same as this. And if we take now a look at the definition of continuity, as I just gave in the previous remark, this shows the continuity of f, because now here it's really the whole D. So this means capital A doesn't play any role here anymore. So this shows that f is continuous in A. Okay, which concludes the proof. So this shows really that continuity only depends on things happening in small areas next to the point. This has one immediate consequence. I will formulate this as a corollary 343, namely for one of our favorite choice of functions, namely power series. We take, so the series a n x to the n be a power series with radius of convergence rho. Okay, and I just assume that rho is non-zero. Then we can define f as a function on B rho around 0. So this is the open circle of radius of the convergence radius here, and we know that inside the circle everything converges. That was the definition of this radius of convergence. So this means f is well defined on this open circle, so to say. So f goes to C, f of z is the sum n from 0 to infinity a n x, f of x, a n x to the n, then this map is continuous. Okay, if I now had an audience, I would ask a particular, one particular thing. The radius of convergence can also, of course, be infinity. This is where I haven't defined this really, and I just put b plus infinity around 0. This should just be all of c, because then we know that it converges everywhere. For example, the exponential series. Okay, so we have this corollary, and this is now, if we take a look at this, and if we think back, if I had an audience, I would now ask a particular question. Haven't we seen this already? Wasn't there something about continuity of power series? Yes and no, because we've only shown parts of it. We've shown that if we restrict to some closed disk here, so the inside of a circle plus the boundary circle. So if this closed disk was lying inside our circle here, so if we would have some closed disk whose radius is strictly smaller than rho, and we restrict to this closed disk, then our function is Lipschitz continuous there. This is what we've proven in section 3.1, so that power series are Lipschitz continuous on these closed disks. But this doesn't show that it's continuity everywhere, so what happens if we go outside these points? In fact, one could show that on this whole thing, it doesn't need to be Lipschitz continuous. There are some examples where this really doesn't work, because simply also these phenomena of something exploding to infinity or something, this can also, there are examples where this can happen, but I won't go into details on this. Anyway, so this, we need to show that it's continuous everywhere. So we can just treat this as a continuous function on this whole circle, on this whole domain where its power series is convergent. And we just can treat this decently continuous functions, and we don't need to worry about restrictions to closed disks or something. Let me erase and then we'll prove this. We will prove this using this restriction argument from the previous theorem. So the idea is kind of to restrict to a domain where we know continuity, namely to closed disks. We have some open disks, so we have, if we take an arbitrary point inside this open disk, this is b rho around 0. So we know that there's, we only know that the absolute value of this is smaller than rho. But the good thing about the real numbers is that there are so many of them. Namely, we can always find some radius which is kind of bigger than the value of a, such that we are inside this closed disk of radius r. But if we're inside this closed disk, there we know Lipschitz continuity. And if this closed disk, if we can show that this is a neighborhood of that point, then if the radius is fine, then we know by the previous theorem that also the big F, F itself has to be continuous in A. So this is what we're going to do now. So we take a radius which is big enough. So we take R inside the open interval from the absolute value of A to rho. We know that this interval is non-empty simply because of this inequality. Okay, so we have R in there, and we put our small r, which will then be the radius of the open disk, which is contained in our in the big disk then, as we shall see. This might sound a bit mysterious, but I will explain this right now. We just take the difference of r and the absolute value of a, and so this is some positive number, which might be pretty small, but anyway. Okay, then we want to show that the whole circle of radius small r around this particular point A, that this is contained in the whole closed disk around 0. So this means then for all x in the open disk of radius r around A, we can make the following computation, and this is simply the triangle inequality again. The absolute value of x, this is smaller than or equal to the value of x minus a to the absolute value plus the absolute value of a. Okay, so since x is inside this guy, this means that this here is smaller than r, so this is smaller than small r plus the absolute value of a, but by definition this is simply capital R. So this means the absolute value of this is smaller than or equal to r. So this means we are inside the disk of radius r, the closed disk, around 0. So since this was an arbitrary point, this shows that br around A is contained in dr. And I simply called this dr before, if this was this closed disk around 0. So this is dr around 0. Okay, so this shows that dr dr is, sorry, I just made a mistake. This is then indeed a whole neighborhood, a C neighborhood, so this domain can be chosen to be everything, a neighborhood of A. And we've seen before that, by theorem 313, the restriction of f to dr, which we didn't call like this before, but this is what we considered, the restriction of this to this closed disk is Lipschitz continuous, so it's continuous. And so since this is a neighborhood, so these two together, this shows by theorem, already forgot the number, 342, that f is continuous in A. And this is what we wanted to show. Okay, so now we know a nice property of power series. So we needn't worry about continuity as long as the power series converges. Everything is nice and continuous. Okay, so this was kind of the end of the prelude. So the idea is now that we have this local nature of continuity. But now, now it's what we will come to limits. So we've now considered restrictions. As the next thing, I want to consider extensions. And I want to start by asking a simple question. So if I have some continuous function on some subset of C, it doesn't matter which one, just as a motivating question here. So if this is continuous, and if I have some point which is in in C but not in D. Okay, I can now, of course, find an extension of D to D with the union of A. So I want to extend this to the point A. But the question is, can I do this continuously? If there is such a point, is there continuous, and this is now the important word here, because an extension I can always just write down, a continuous extension G from D united with the point A to C, a continuous extension of F. Does this exist? Okay, I can just always write down some extension, because I can just, if I just want a map and I don't care about continuity, I just assign any value I want to this A, so some fixed value, and I have a map. Of course, that's trivial. But what happens with continuity? And there you can see, and this is something I don't want to discuss in detail because it's kind of not that important for us. If A is kind of far away from this D, so let's say D is some circle and some disk, and A is some point far away from this disk. Then I can also just define any extension and I get continuity, because continuity depends only on this local notion, and if I just only have this one point somewhere far out and nowhere near, there's no criteria for continuity, so it just continuity immediately follows, like trivially in some sense. So this is not really interesting, but what happens if A kind of touches this D? So if we have some subset D, for example, we have an open disk, and we have a point on the boundary, which is not contained in this open disk. But can I continue this to this point on the boundary? And can I do this continuously? In general, the answer is no. Just some initial motivation. So in general, no. If we consider the function, and I will not prove this in detail, we take the open disk of radius 1 around 0 to C, and this is again a power series. F of x is the sum from 0 to infinity of x to the n to the divided by n. We've seen before that this has convergence radius 1. This is what we've proven. So the radius of convergence is 1, but can we continue this to boundary points in here? But it turns out there are some boundary points where we can, namely if we insert -1. So here, this only with respect to this example, can extend continuously to -1. Since we know that if we insert -1 here, -1 to the n divided by the power of n, divided by n, this is this alternating harmonic series. We've already seen this, and there the Leibniz convergence test shows that this thing exists, and you can see that this is indeed continuous. That's something you can show. But what happens at another point, namely at the point 1? If we just insert x equal to 1, then we just get, this is 1 over 1 to the power of n, so we just get the sum of 1 over n, the harmonic series, which is divergent. And so this becomes infinitely big. And this kind of shows then, and this is something I won't do in detail here, that if I come close to this point 1, I cannot continue because the values of f will explode. So this will become something crazy, but it will not kind of converge to some nice value. So we cannot just extend this continuously. So can you extend continuously to 1, to minus 1, but not to 1. This is something, so we will not prove, but just intuitively, this because this harmonic series diverges here. This is precisely the case at this point. So the bad news is that we cannot always find such continuous extension. But the good news is this gives us rise to consider some nice mathematics, because now we can ask, when can we find such a continuous extension? And can we find good conditions for this? Okay, but before we do so, we need to introduce some terminology, because I was a bit sloppy. Here I just said that the point A, the idea was kind of that A touches D. This is, of course, not a mathematical definition. So let me first give a mathematical definition of this touching phenomenon. So, definition 344. A is a subset of C. A point A in C is called an adherent point. I think adherence is also a physical term, so it's kind of a point A which is glued to this capital A in some sense. An adherent point of A. Okay, what does this mean? So we're this is extremely close to A. So how do we formulate extremely close? So as close as it gets. If for each epsilon bigger than 0, we can find some x in A which is epsilon close to A. So with x minus A to the absolute value smaller than epsilon. So we can come arbitrarily close to this point small a inside the set capital A. And if we can just formulate this with our open balls again, this just means that B epsilon around A intersected with capital A is non-empty. So this would be kind of the small naked truth about these sets, and so you can just formulate this concisely. Okay, so if such a thing exists, then secondly, while I'm at it, I define the set A bar. This bar has nothing to do with complex conjugations. Unfortunately, we have the same notation here, so I'm just using this because this is the standard notation, so please don't worry. The set of all points which are adherent to A is an adherent point of A. So this set is called the closure. The closure of A. Okay. We've talked about closed subsets before, and here now we've got closure, so this suggests that these terms might be related, and they are indeed, as we shall see in a little bit. So this is a set of adherent points. And now a little remark just to understand this closure a little better. So first of all, every point in A is contained in the closure. So A is a subset of A bar. So every point in A is an adherent point of A, and this is easy to see. Namely, so we need to show that these intersections here are non-empty, but if we take a look at B epsilon of A intersected with A, if now the point A lies in the set A, this definitely contains A itself. So this is a set which contains the set with the one point A, and this is of course non-empty. So if this is contained, this is not empty. So this for all A in A and for all epsilon bigger than 0. That's good news. So every point in A is an adherent point of A. Okay, but so this this is always a subset. The question is, of course, is this an equality? And the answer in general is no. But in general, A is not equal to the set of its adherent points. And just a simple example, I mean, I just mentioned this case of this open disk, and you take a point on the boundary of this open disk, which is adherent, which I won't prove here now, but a very simple situation, to think even that's a little simpler. If we take A to be the half-open interval from 0 to 1, where 0 is missing, 0 is an adherent point. Because if I take any interval around, any of these sets here would then be the intervals, B epsilon of A, the real part of this, so the part of the limit lies in R. This will be the interval minus epsilon epsilon, if I take this around 0. And minus epsilon epsilon always intersects the set, obviously, because 0 to epsilon, this open interval is included. And so, we can get arbitrarily close to 0. That's the idea here. So 0 is really adherent, it's kind of glued to this big set, capital A. So for this, 0 is an adherent point. If you want to do a nice little exercise to understand these things better, just pause this video at this point and really formally prove that 0 is an adherent point using the definition. Okay, so this is an adherent point. First part of the remarks. Second part. Okay, how can we characterize it then? So we know that we have this set of adherent points, but of course, using this definition, this is hard to realize in some sense. And there's another nice characterization, which I will use but not prove here. But this is kind of also easy to follow from if you understand kind of how these things with epsilon neighborhoods work, with these epsilon boards work. Namely, a point A is in the closure of the set A if and only if the following holds. There exists a sequence in A, so xn and an n, sequence in A such that the sequence converges to this adherent point. Okay, so this is kind of the sequence version of becoming arbitrarily, the set becomes arbitrarily close to this adherent point, right? So this is maybe a bit simpler. So all limits of sequences in A which converge. So if we have all these limits inside. So this shows, this is something I can squeeze in still right here because this is very simple. This shows a simple thing. A coincides with the set of its adherent points. By this characterization, this is the case if and only if all limits of sequences are inside. And this is something, so inside of A. And this is something we've already defined. Namely, this means this is equivalent to A is closed. So the closure is kind of making this closed in some sense a set. And if it's already closed, the closure doesn't change it. So the equality only holds if and only if the set A is closed. This is simply by putting definitions next to each other. Let me quickly wipe out everything I've written. As a final part of this remark, I want to mention something that I want to write down something that I've already mentioned verbally, namely the following: if we have some continuous function on a domain D. So if this is continuous and we have an adherent point A, so A is in the closure of D, then a continuous extension does not need to exist. So a continuous extension to D united with A does not need to exist. And I will give you a very simple example. I mentioned this example involving this harmonic series before, but I give you a simpler one. Give you a simpler one. Namely, we consider the following function. We take R, but we take away 0. So this set is, of course, it's easy to see that the closure of this set is the whole set R, since we can come arbitrarily close to 0 inside of R without 0, that's clear. So 0 is really an adherent point here. So f goes from R without 0 to R, and we say f of x is 1 over x. This is probably a function that every one of you has seen in high school. That's this hyperbola at the graph. So like this and like this. Okay, very basic. So this function, here we can see that we don't have a continuous extension to 0 because, so here would be x f of x, sorry, it's always label the axis. And yeah, we can see if we approach 0, we either go to plus infinity or to minus infinity, but definitely we cannot just find a continuation, because if there was some point such that the whole thing would be continuous, these values would need to converge to some fixed point and to the same point from both sides. And this obviously doesn't happen. And yeah, this is kind of what we can formally do. Maybe do it very simple. So this f has no continuous extension to R. Namely, if it was continuous, if we take a sequence which goes to 0, and for example we take 1 over n, our favorite sequence going to 0, then we would need that the limits of f of 1 over n, that this would converge as well. But 1 over n is of course n, so this is limit of n going to infinity of n, which is obviously plus infinity. So this diverges to plus infinity and can't converge. So we cannot have a continuous function which restricts to on all of R, which restricts to f. So yeah, this is divergent. That's the important thing here. Okay, so this shows that we cannot always have such a continuous extension. Let me go on a bit with continuous extensions, and then we will see examples of continuous extensions in a bit, so don't worry, it's not only theory. First of all, a thing which is kind of quite obvious, so to say. So, for example, a situation where such a continuous extension would exist would be if we would have such a function. So let's say we have some value a which is missing from the domain, and let's say we have R without a as the domain. So assume we have some function which would, I don't know, do something interesting, I don't know, that's continuous, but there would just be this slight gap here. So this point would be missing. So here would be like, don't have a value. But here we see, like everyone can see what I have to fill in. I just have to fill in this particular value which is missing here at the point. So there's only this point which can make it continuous. If I would fill in anything else, we would obviously have some jump. So it could not be continuous. And this is a general phenomenon. So here we've got this with subsets of C. So in general, kind of, if I can fill in something continuously, then it's unique. Then there's only one particular value that I can fill in, so it becomes continuous. And so let's see this and let's prove this. So we have a domain, a subset of C. We have a continuous map on D. And we have an adherent point of D. So if there exists a continuous extension, if there exists a continuous extension G from D united with A to C, then it is unique. So there can only be one. Okay, and this can really be explicitly proven, and the proof is also not too hard. So first of all, if A is an adherent point, and we know that the set of adherent points consists of the domain and the additional points, but if A lies inside the domain D, then there's nothing to show, because F is already the extension. It is already defined there. So if A is equal to D, then necessarily G has to be equal to F. So D united with A is just D. And then G is equal to F. Hence, it is unique. So it cannot be anything different. So this is the trivial part of the proof. Okay, now for the non-trivial part. What if we have a really proper adherent point? So assume that A is not contained in D itself, but only in the closure. Not inside of D, but only in the closure. And assume we have two different, or not necessarily different, but assume we have two continuous extensions, G1 and G2, from D united with A to C, be continuous extensions of F. So to show that it's unique, we need to show that these two coincide always. So how do we do this? First of all, we define a third continuous function, namely H, which goes from D united with A to C, h is simply defined by g1 minus g2. And since g1 and g2 are continuous, h is continuous. Okay, this is what we know, but how does h look like? What does it look like actually? So let's write this down explicitly. H of x. So both of these maps, g1 and g2, are extensions of f. So this means that on D itself they have to coincide. So there g1 of x has to be g2 of x, so both have to be f of x. So this means the difference of them has to be 0 if x is in D. Okay, and if we are in A, a priori this could be anything. So let's call the number C if x is equal to A, where C is simply defined as the difference of the two values. So g1 of A minus g2 of A. So this is the only point where these two functions could differ. And so what we need to show now is that C is 0, that this has to vanish. And this is what we now do with the continuity. So since, sorry, it's not, yeah, it's continuous, sorry. Yeah, everything all right. Okay, so since H is in particular continuous in A, so let's write this continuity. For all epsilon bigger than 0, there exists some delta bigger than 0, such that h of x minus h of A. Now we write this with our new favorite formalism. For all x in B, delta of A intersected with the domain. Intersect with, well, yeah, D united with A. Sorry, yeah, this, oh, smaller than epsilon. Okay, so this is our new favorite way of writing things. So, in particular, so this is what the definition of continuity says. But this in particularly shows that if we just forget about A, that this is also true. So this is not continuity, this is something slightly weaker, but this is a true statement. But if we now know that we are in D, we know that h is 0 at x, and this is a fixed point. So this would be 0 minus c to the absolute value, which is, of course, just c. But this means we've shown that the absolute value of c is smaller than epsilon for all epsilon bigger than 0. This can only be the case if the absolute value is 0, and this shows that c is itself 0. And this shows g1 is equal to g2. And this is what we wanted to show. So this is the uniqueness of this continuous extension. Okay, so now we know if we have some continuous extension, it will be unique. There can only be one. So this kind of gives, and this is the reason why I put the examples a bit later, about the following important definition, which is then actually well defined. Namely, assume we have a subset of C, we have an adherent point of D, and we have a continuous map on D. Okay, and we now say that f has a limit in A if there exists a continuous extension G from D united with A of f. And then we put the following notation. We then put the limit of x, sorry, I need to write this properly because that's the first time, the limit, but now x going to A, and this is not purely symbolic at the moment because we haven't kind of introduced limits only for sequences, but I just define the limit of f of x as x goes to A. This is the way we speak it. So limit of f of x as x goes to A. This is then defined as the value of the continuous extension at A. So g of A. This is the limit of the function in the point here. And this is why I now only introduce this at this point, because otherwise it wouldn't be well defined. Here we know, let me just add this, so just let me write this down once. This is well defined since this extension is unique. So this value of g can only be one particular value, and the other ones So there can't be more of them. So this is well defined by theorem 346. So otherwise we wouldn't have the notion of limit. Okay, now enough of theory. So now let's treat ourselves and see two nice examples. So I will now compute two different limits of functions, and then you maybe get some more intuition about how this all works. And this is basically important for this understanding here. You will also compute further examples in the exercises. I will compile some nice ones, but we will now see two quite instructive examples of this. Okay. Whoop.